Hello, in this video we're going to figure out how we can find the center of mass of a lamina. Now, a lamina is just a fancy word for a big flat sheet. We're going to consider it in two dimensions only. So we can think about it in terms of a big flat sheet that is kind of bounded by functions and by some bounds on each side. Let's see what we can get in terms of a look at this. So let's consider this. We've got ourselves the xy plane. There's our y-axis. Here's our x-axis. And let's pretend that there are two functions. It really doesn't matter what they are, but we've got function f of x and function g of x, like here. And let's put some bounds on that function. Let's say that we're looking at that function from a right here to b right there. So basically I'm asking, if we have this two-dimensional plane, we can find this area in here fairly easily, but then what is the location of the center of mass of this plane? This is a little bit more complex than finding just the area because we have to take into account the mass of the whole thing as well and figure out where the center of all that distributed mass is. Now, for the sake of simplicity, we're going to assume that this entire field is of even density, but we could easily see if it was not even density where we could pop in a function for the distribution of the density. So let's take a minute to recall what we've talked about before in terms of center of mass. Previously, to find the location of the center of mass, we've taken the first bit of mass times its location plus the second bit of mass times its location all the way up to the nth bit of mass times its location, whoops. And we've divided it by the total mass, like that. So this was pretty easy if we had only 2 or 3 bits of mass, but unfortunately we have lots of bits of mass in a lamina, so it would be impractical to try and figure out where the locations of all of these are. Fortunately, we have something right here. That is called a moment. And recall, a moment is simply some quantity multiplied by its distance to a particular location. So we can use that concept, find a bunch of moments, add them all up, and we can figure out where the center of mass of a lamina is that way. Now, keep in mind, we have 2 dimensions this time. Previously, we were working in pretty much 1 dimension. We've got 2 dimensions, so we're going to need moments in both directions. So let's see what we actually need. We need the total mass, and we need to find the moment with respect to the y direction and the moment with respect to the x direction. So we need both of these, or all 3 of these things rather, in order to find the center of mass of our lamina. So let's look at the mass total first, because I think that's the easiest way to start. And I think the best way to do this is to break up our lamina into thin strips like that. So let's draw it. Here again is our lamina. There's our first function, f of x. Here's our next function, g of x, that bound this lamina. And instead of looking at the entire thing from A all the way over to B, let's just look at a very thin strip of mass in here. We'll call this location x, and we'll call this location x plus dx. We just added a little bit to it. Now I've exaggerated how big this is, ideally, and probably you can see where this is going. We want to make sure that this strip gets as thin as possible to make our slices as small as possible and make our integral as accurate as possible. So we're really going to let the thickness of this strip go to 0, but for now, let's draw it somewhat enlarged like this. So we know then the distance right here is simply dx. And if we wanted to find this distance right here, because remember we've got to find the area of this whole thing first before we can do anything with mass, this area would simply be the difference between the 2 functions. It'd be f of x, or this distance rather, minus g of x, like so. So we kind of have an idea of what this shape looks like, and we can guess that the center of mass of the strip is somewhere in there. So we just need to figure out exactly where that is, and then if we know that the strip is infinitesimally thin and we let it go down to 0, the thickness of it at least, we can add up all of these infinitesimally thin strips, figure out where the center of the mass is for each of them, and then integrate that one more time to figure out where the center of mass of the entire lamina is. So let's start with the total mass of the strip because we need that. And that seems like a reasonable place to start. So to find the entire mass, we're going to use surface density. Now, surface density is the same concept as regular volumetric density, except we're dealing with a 2D object. So density in 3 dimensions is mass divided by volume. That's 3D right there. Make sure that looks like a D and not a P. And in 2 dimensions, though, if we're dealing with surface density, rho equals simply mass divided by area. This is in 2 dimensions. Again, can't seem to draw a reasonable, D. At any rate, we're going to use this formula right here. So we need the mass and we need the area if we want to figure out density. Generally, though, we're given the density and we're given the area, and we can substitute that in for mass. So if we reorganize that, we simply have density times area equals mass, which is a pretty useful thing to have hanging around. So for the density of this, let's consider now just one strip of mass, not the entire lamina. The density of the strip is just given. We'd have to give that to you. The area of the strip, though, would be the length of the strip times the width of the strip. Well, that's pretty straightforward since we've already defined these two things. I'm going to flop back to this other slide right here. We've already defined that the width of the strip is dx, and the height of the strip is f of x minus g of x, the difference between those two functions. So this ends up being that times f of x minus g of x, like that. That's a really good expression for the area of the strip, right here, times the density, and that will give us the entire mass of the strip. Now, if we want to find the mass of the entire lamina, all we have to do is substitute in all the possible x values here, run them through the function, and that sounds an awful lot like an integral, which indeed it is. So for the entire lamina, then, all we do is we take the expression that we came up with for mass and we integrate it over all the possible places that we have. So the mass total here would be from A to B, not just the strip this time, of the area density times f of x minus g of x, like so. All of this with respect to x. So this is an expression for the entire density of the lamina. Now, if we're assuming that this right here is a constant, we can pull it outside of the integral. At this point, though, if you did see that there was a function that described with respect to x, or with respect to y for that matter, how the density changed, we could substitute that function right there. But for our purposes, we're going to assume that the density remains constant because it makes the math just a little bit easier. So the total mass, we can pull this out in front, is the integral from a to b of f of x minus g of x with respect to x, just like that. So now we've got that. We've got the entire mass of the entire strip. We've got to figure out, though, the x and y directions, what the moment is, because, and I'll flip back here, remember what we were talking about before. If we can add up all these moments right here, we've already got the total mass right there. If we can add up all the moments, we can easily find the location of the center of mass in that direction. So let's do that. I think what we need to do is think about what the coordinates of the center of mass of that strip might be, and then integrate that over a larger area to see what we can find. So let's look again. Let's look again, not a curvy axis right there, at our two functions, f of x and of g of x, like that. And let's look at our thin strip right here, and let's pretend we know the center of mass is right there. We already know this distance, it's dx, because we've already taken this location, called it x, and this location and just called it x plus a little bit. So we know that that little bit would be the width here. So if we want to find the location in the x direction, it would simply be the middle of these 2 points. So in the x direction, we'd simply have x plus dx, a little bit like that, and we divide it by 2, and we can find the location in that direction, because it would be in the middle. Essentially, we're finding the average of those 2 things. In the y direction, we can do something very similar. I'll flop back here. We know that if we have a point here and a point here, this would be the value of the function, the y value of the function at that point. This would be the y value of the function at this point. If we add those 2 together and we take the average, we should have the y location. So let's do that. We'll take f of x plus g of x, divide that by 2. So now we've got some coordinates of the center of mass for both of these things, which will be a pretty useful thing to have hanging around. Because if we have the center of mass of the lamina, if we can integrate over all of the values of from a to b, we can figure out the center of mass of the entire thing. So next, let's do the moment in the x direction. And this is with respect to the x-axis, rather. So with respect to the x-axis. So basically, I want the distribution of mass around the x-axis. If here's our x-axis, and I want to know where all these bits of mass are located, really what I want to know is the y distance right here. I want to know that distance from all of the individual pieces of mass to the x-axis. This will give me the distribution of mass with respect to the x-axis. So really, I need to know the y-coordinates of all of these little pieces of mass. Well, that's very fortunate, because we just figured out that the coordinate of the center of mass for that strip is the average. So x plus dx like this, divided by 2. That's the location of the x location of each coordinate of mass, but that's not what we're looking for right now. We want how far it is from the x-axis, which would be the y-coordinate, so we can just simply take f of x plus g of x, divide that by 2. This is the thing we're looking for. This is the distance to the x-axis. So that's what we'll need to employ right here. We've got the distance. And remember what a moment is. A moment is simply some quantity times some length, or some distance to some particular thing. So in our particular case, the quantity is mass, and the length is the distance to the x-axis. Well, fortunately for us, we already have an expression for mass. It's the density times f of x minus g of x. And we already have a distance. It's the distance to the x-axis, rather, which we said would be the coordinate of the y center of mass for this particular strip. So it's f of x plus g of x divided by 2. So all we've got to do is multiply these 2 things together, missing a parentheses right there. So right here, we've got a binomial and another binomial. We FOIL those together. We've got different signs in the middle. So the middle terms, the negative g of x, f of x, and the positive g of x, f of x, will cancel out. And all we're left with is this. We're left with that times f of x squared minus g of x squared, like so. Oops. And we'll divide this whole thing by 2. So that makes an awful lot of good sense so far, I think. I realize also I missed my dx's in here, so we'll have a dx like that. So now we have an equation for the moment in with respect to the x-axis, but this is simply the moment of the strip. We want the moment of the entire lamina, so we've got to integrate it over our entire range. So for the lamina, doesn't exactly look like an A. For the lamina, what we've got to do to find the moment with respect to the x-axis, if we're going to integrate this over the entire distance. So I'm going to do this, the integral from A to B of rho times f of x squared minus g of x squared, all divided by 2 with respect to x, like that. Now we can tidy this up a bit, because notice here, we're going to assume that that is a constant. And just like we did with the mass before, if we assume that the density is constant, we can take it outside of the integral. So a nice expression for the moment with respect to the x direction is this. We'll take the density outside, integrate over our bounds from a to b. We'll take the 1/2 over here just to tidy it up a little bit so we don't have that giant fraction. F of x squared minus g of x, that whole thing squared. Make it very explicit, and dx like this. So here's the moment with respect to the x-axis. Really what this is describing is the distribution of mass around the x-axis. So it's the y distance of all of those individual masses from the x-axis. If you imagine that the x-axis is a line and you put mass above it or below it and you pushed on that mass, it might rotate around the x-axis. But the important thing to remember about this particular moment, it's describing the location, the distance from the x-axis. All right, so let's do the same thing, but because we have 2 dimensions, we've got to do the moment in the y direction. So we can have the same idea here. This is simply the distribution of mass with respect to the y-axis. So as before, we really need the distance from the x-axis. Let's start with just the strip to begin with. And remember, we can consider all of the mass at the center of location, the center of mass of that particular strip. And once we do that, we can integrate over the entire value from a to b and figure out what we get. So remember that the location of the center of mass of the strip was x plus, x plus dx divided by 2, comma, and this was f of x plus g of x divided by 2. We already used the right side of this, the y-coordinate, to figure out the moment with respect to the x-axis. Now that we're dealing with the y-axis, we need to use the x-coordinate like that. So that is the location around the y-axis of where all the mass is located. Graphically, it would look something like this. Here's the y-axis, here's the x-axis. If I have all these individual bits of mass out here, I want to know, with respect to the y-axis, what are all these distances? Well, this is pretty straightforward because that just ends up being the distance to the y-axis, which is simply the x value of that coordinate. Remember what we're going to do. If we take x plus dx and divide by 2 to find the average location of that, we're going to let dx get really, really, really small. In fact, we're going to let it go to 0. And so this just ends up being the x-coordinate. So this equation ends up being a little bit more straightforward than the moment for with respect to the x-axis. So remember, a moment is simply the mass, in this case, times some length. Well, the mass we already have an expression for. It's the density times f of x minus g of x dx. And the length this time is just x. So for the strip, the location of the center of mass is simply x rho times the quantity f of x minus g of x, like so. But if we want the location of the entire lamina, the center of mass of the entire lamina, with respect to the y-axis, we've got to integrate over all of those possible values. So the moment with respect to the y-axis, in this case, is going to be the integral from a to b, that times x times the quantity f of x minus g of x, with respect to x, of course. Now, again, we've said that if there was some sort of function that described the density, if there was a density gradient, if we knew what that looked like, we could add the function in there. That would be relatively straightforward, so long as the function was in terms of x, so we could integrate. But because it is a constant, we can pull it outside the integral like this. So we have x times the quantity f of x minus g of x with respect to x, like so. So now what do we have? Let's just summarize briefly. We have an expression for the total mass. we have an expression for the moment with respect to the x-axis, and we have an expression with the moment respect to the y-axis, which we just figured out. So now all we need is the coordinates of the center of mass of the lamina. So let's recall a couple of things, right? Previously, when we've talked about center of mass, the location of the center of mass has been given by, if we take all of the moments and sum it up, so we're going to take from I equals 1 to n of mi xi, like so, and divide it by the total mass, this would be the location of the center of mass. But keep in mind what we're doing here, right? This is the location on the x-axis. We're assuming only one dimension. In this case, when we have a lamina, we've got 2 dimensions. So the moment y describes the distance along the x-axis and thus the x-coordinate of the mass. Think about that again. The moment in the y direction, the moment with respect to the y-axis, describes the distance along the x-axis because it's the distance from the y-axis, which would be the x-coordinate. And so the moment in the y direction must use the x-coordinate of all these individual parts of mass that we're adding up here. So we use the moment with respect to the y-axis to find the location of the center of mass of the lamina in the x direction. That seems somewhat counterintuitive, but when you go back and look right here, the moment with respect to the x direction, we have the mass on the left side, the moment with respect to the y direction, the y-axis rather, we have the moment on the left side. All we have right here is x. That's the information we're looking for if we're trying to find the x location. So somewhat counterintuitively in terms of how they're named, in terms of the syntax, we have to use the moment with respect to the y-axis to find the x-coordinate, and we have to use the moment with respect to the x-axis to find the y-coordinate. So if we put this all together, to find the location of the center of mass for the entire thing, the entire lamina, we're going to take the moment with respect to the y-axis and divide it by the mass total, and that will look something like this. The moment with respect to the y-axis, remember, is the x distance from all of these things, so we're going to take the integral, we're going to bring the row outside as before because we're going to assume that it is constant, from a to b of x times the quantity f of x minus g of x with respect to x. And we're going to simply divide that by the total mass. So that's, again, the integral from a to b of the quantity f of x minus g of x, like so, with respect to x. So what you'll notice immediately is if the density is constant, the density will cancel out and we don't need to really worry about it. Again, if the density was not constant, we could leave it inside the integral so long as the density was a function of x as well. So here is the equation, finally, for the x location of the center of mass of that entire lamina. For y, we'll have the moment in the x direction divided by the total mass, and that'll look something like this. We'll have the density outside the integral again. We'll go from a to b. We have 1/2 times the quantity f of x squared minus g of x squared with respect to x, and we'll simply divide that by the total mass. Take the density outside because we're assuming it's constant. A to b times the quantity f of x minus g of x with respect to x, like that. And again, the densities will cancel out as so. So now we have all the information that we need. We have the moment with respect to the y-axis, which we can use to determine the x-coordinate of the center of mass. We have the moment with respect to the x-axis, which we can use to find the y-coordinate of center of mass. And of course, we had an expression for the entire mass of the entire lamina. I hope this helps. Thanks.